Hey guys, it's Devin. We are working on the lesson 5 group problems today, and we're just going to jump right in with number 1. We're looking at gene linkage today. And so for this problem, we're looking at the mice with the mahogany color, mahogany, agouti, and ragged genes. So I'm just going to start by kind of recreating the table that was given in the problem. So RG, and my plus in this case is going to stand for wild type, one of those offspring. So we're going to put all of our alleles over here and the number that express that. So then next we have a wild type color with a mahogany. There is one of those. Next we have an agouti, wild type. 13, we have wild type, RG, NG, 12 of those. Wild type for all 3, there were 16. Recessive for all those, there were 18. We have A plus NG gives us 76. And then plus RG plus gives us 69. Okay, so yeah, you can see that our 2 largest categories are down here at the bottom, and these are going to be our parentals. And then our 2 smallest categories are up top, and these are going to be our double crossovers. Or, excuse me, DCOs. DCOs. So part A asks us to determine the allele arrangement in the heterozygous parent. Well, that's down here, these parentals. And so for part A, let's put that right here. Our genotype to be A plus MG plus RG plus. And so that will be our answer for A, the allele arrangement in the heterozygous parent. Now, for part B, we need to look at the gene order, the parents. And so in this case, we have to kind of compare our parental mice with our double crossovers and see kind of what the difference is. And so comparing this one and this one, the only difference between these 2 is going to be this A. So where there's an A here, there's a plus and an MG, so that matches. For the other parental, the only difference again is the A, and we have an RG and a plus, so that matches. So that means the gene order, our A has to be in the middle. So for part B, we'll kind of just rearrange these things, and so we'll put our plus A and G, and then over our RG plus. And so that's kind of the gene order, the A in the middle. Over here is where I'm going to jump into part C. We need to construct a linkage map showing the distances between the genes. Well, before we do that, we need to do a couple of other things first. We need to solve for the distance between the A gene and the R gene guy. Okay, and that is always recombinant over the total. You see that? So we have both of our double crossovers, 1 and 1, and then there were 206 total mice in this problem. Sorry, I didn't do that earlier. And so we've accounted for our double crossovers. Now let's kind of look at our single crossovers. And I'm going to mark all these with a star. So here are double crossovers. Now let's just look for the single crossovers. Now, they are going to be right here, our 16 and our 18. So if this were to be our double crossover, if we were to flip this back, we'd be left with all positives, or excuse me, all wild types right here, and then all the recessive genes. And so we can find those 2 right here. And hopefully you can see that these two can be obtained by simply flipping the mahogany trait over. And so we're going to put our 16 and our 18 right here, which will give us 36 over 206, and we'll multiply that by 100, which will give us about 17.48 MU. And so that's the distance between the AG and the RG. So similarly, we're going to have to compare that to the MG. Again, that's the recombinants over the total, which again is going to be our double crossovers, 4 plus 1. And then the only ones we haven't really accounted for are these, the 13 and the 12. So those are going to come in here over our total 206. And math-wise, crunching the numbers, that's going to be 27 over 206, which will give you 13.11 MUs. Okay, so just to clear up some real estate real quick, we'll insert part C right here for you. So part C is asking us, again, to just construct a linkage map. And with our proper gene order over here, well, we have to have A in the middle, so let's just put RG, A, and then MG, and we just calculated the distances between them. Between A and RG, we have 17.4 MUs, and we can just do some dots to connect those. Between A and the mahogany, the MG, again, a couple dots, that's 13.11 MUs. And so there is kind of your linkage map. You can also, you can look at it like this as well. You can go the RG to the A to the MG and have these like approximate distances. We'll call that R17.4, and we can call that R13.11. So whichever way you want to do it, both of those are valid linkage maps. Part D is asking us to calculate the interference. We'll do that right here. Interference is 1 minus the observed over the expected double crosses. And so in order to kind of calculate how many double crosses are expected, remember that's going to be the product rule of both of these probabilities. So we'll put this back in its decimal form, 4. And we need to multiply both of these, I guess, the distance and the frequencies end up being kind of the probabilities, which is really nice. So we'll go 0.1311. And that gave us, let's see. And so probability-wise, it's going to be 0.0229, and you need to multiply this by the total offspring to then find the number of expected double crossovers. So multiply this guy, total 206. 6, and that means our expected double crossovers would be 4.7. Let's round that up to 5 expected double crossovers. And so let's just come right here. 1 minus, we actually observed 2 double crosses over 5, which is going to give us 6 or 60% of our double crosses were impeded. Remember, we're calculating an impedance, which means 40%, or the 2 that we observed, double crosses actually happened, 60% of them were impeded. So that'll wrap up number 1, and we'll pass this marker off to Tanner for number 2.
All right, for number 2, let's start off by redrawing the table for these fruit flies. So to determine the parental genotypes, we'll just look at these. The number, our largest number is just the 314 and the 280. The double crossovers will be the genotypes that happen least frequently. So it will be the 10 and the 14 down here. So for number A, we need to figure out the arrangement for the heterozygous parent. And we'll just take these genotypes right here for the parental alleles. In order to determine the gene order, we'll find which one of these genes switches over the double cross, and that will be our middle gene. So by looking at the parental genes and the double crossover genes, we can see that the SC gene is the one that flip-flops places. So down here, well, up here we have SC wild type, then SV. Down here, our S and V are in the proper order, but the SC wild type flip-flop down here. So we'll place that as the middle gene. All right. Next, we'll figure out the map, the linkage map that'll show the distance between these genes. So we'll start by looking at the first and second genes. And we'll do the recombinant over the total number of offspring. The total number of offspring is 1,000 for this. And let's see, we'll mark these all with a star. So the middle gene is SC gene. When it crosses over, that's the double crossover here. So we'll put a star on that. And then we'll look for where the S gene crosses over. So if we flip-flop the S gene on the parental, we'll end up getting SC wild type, S wild type, and then V recessive. And we find that right here. And then if we do the same thing just for the other side, we'll turn out that this is the complementary offspring. So we'll add all these numbers together. 150 plus 156 plus 10 plus 14. And we multiply that by 100. And that'll give us approximately 33 MU. We'll do that for the middle and the last gene now. Very similar method. We'll use a triangle to mark our different offspring. So once again, the double crossovers, we'll use them for the middle gene. And then we'll take these two genes, they're the only ones left over. So they're going to be the offspring that happen when the third gene is flip-flopped. So if we add all these together, we'll end up getting 46 plus 30 plus 10 plus 14 over 1,000. Multiply that by 100, and we'll get 10 MUs. So to write our map, we'll do it right here in the middle. We'll start with the first gene, S, and that'll be 33 MUs away from our second gene. Which will be 10 MUs away from the final gene. And That's part C. Part D. We'll figure out the interference for the double crossovers. So we'll change our distances between each gene into a probability. Multiply those together. And that'll give us the probability of a double crossover happening. And then we'll multiply it by the total number of fruit flies, which is 1,000. And that'll give us 33. That's the expected amount of double crossovers. And if we look at our chart again, which is still on your paper, we'll find that if we count the observed amount of crossovers, it was 10 plus 14, which is 24. So interference will equal 1 minus observed over the expected. So in this case, that's 1 minus 24 over 33, which equals 0.273. So that'll be the interference value for this problem.
Thank you. So for question 3, we're still working with the Drosophila flies, and again, I'm just going to recreate the table. Only the mutant phenotypes were indicated above, so you have to kind of extrapolate a little bit. Plus, 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 so they were all wild type, plus, plus, and then the S was striped, that's right. Coal body plus GC plus is next, G plus S, GCS. Okay, now let's get some numbers up there. 27 offspring here, 11, 44, 441, and 20. All right, so there are only 6 entries here, and that doesn't quite make sense. We're missing 2 of them, and so we have to kind of fill in the gaps of what we're missing. There should be 4 of each allele in every case, and we kind of have to piece together where those are going to be. So up here at the top, there's actually going to be a plus, a coal body, and then there were 0 of those. Down here, we have G wild type, and again, there were 0 of those. We kind of just had to guess and assume that since there weren't any born, they weren't listed in the table for these particular phenotypes. The glassy eye is wild type for the color and for the stripes. So we got our perennials, and those are the most frequent, the most common, or double crossovers in this case. COs are the least often occurring crossovers, and in both cases, those are going to be 0. So for A, again, we're asked to write the parental genotypes. So let's just say plus with that should be a C for coal. That should be another wild type. Over the glassy-eyed wild type striped thorax. So that's going to be your answer for part A. Part B is asking us to find the correct order of alleles. And let's just look, comparing our perennials and our wild types. The only difference between this parent and this double crossover is going to be this S allele for stripes. Let's look over here at this parent and this double crossover. Again, the only difference, because you have a wild type, coal body, the only difference is in the S striped allele. So that one Therefore, it has to go in the middle. So let's just write this. Again, it doesn't matter a ton. GS plus over G plus C. And I was making up the S allele is in the middle. And so that'll do it for part B. Part C, again, is asking us to calculate and draw out the linkage map. So we're gonna have to start looking at frequencies and distances between these two. So at first, let's compare the G and the S alleles. And so our equation for that is the recombinant COMB over the total. And again, we haven't mentioned it, but we have 1,000 total offspring. Okay. And so that includes both of our double crossovers in this. So that's going to be 0 and 0. And now let's compare the kind of just these single crossovers, if we will. And so it turns out that this parent is going to correspond to this one right here. So we'll start that guy. Because can you see that with me? The SOL is going to be the same. Wild type for the cold color is going to be the same. The only difference is glossy eye versus the wild type. So we're going to need that 11. Now let's compare this parent and the one right below it. Again, the only difference is going to be in this glossy eye color, as we have a wild type for the striped allele and we have the same cold body. The only difference is going to be right here. So then we can put an 11 and an 8 over a total of 1,000, which works out to be, and we'll multiply that by 100, and we're left with 1.9 MUs of distance. Oh, can't even see that on the board, so we're going to put that up here, 1.9 MUs, and we can see that a little bit better. Sorry, guys. And so now we're going to have to compare this next allele, the C and the S. And by the same equation, I'm not going to rewrite that. We'll go 0 plus 0. And the only ones left in this case, since we've taken care of these 8 and 11, we're going to look at that one, 27, this 29 right here. And again, both of our double crossovers. So let's add 29 and 27. Over 1,000 times 100. And that'll give us 5.6. So I'm going to break that over here where we can see a little bit better. 5.6 MUs. Okay, so hopefully you can see that. Part D again is asking us for an interference value. So let's just remember we have 0 DCOs, and there were no double crossovers at all. So let's free up some space for us. Part G, so the interference is equal to 1 minus the observed over the expected. Now, again, using that product rule, we can convert both of our distances back into their probabilities, their percents, so 0.019, and we'll multiply that by 0.056. So I didn't write that down in the calculator. 0.019.0056. And so our probability of getting a double crossover is 0.0011. We need to multiply this by the total number of offspring, which is that 1,000, so that's going to come in right there. And that our expected number of double crossovers is just going to be 1. There's 1 expected double crossover. What we actually observed, though, 1 minus our observed was 0 over the expected 1 crossover. 1 minus 0 in this case is still just going to be 1. And so putting that in a probability, So our answer is 1, but let's think of it as a percent. 100% of the double crossovers were interfered with. For whatever reason, double crossover did not happen in this case, and our best guess, our postulate, is that because these alleles are so close, 1.9 base pairs, if you will, and 5.6, there's really no way that there can be a double crossover. So that will wrap up number 3.
The phenotypes for the corn in problem 4 are 100% determined by the heterozygous parent. So we'll just translate all of the phenotypes we see into the gamete that comes from the heterozygous parent. So starting with the first one, that's all wild type. That'll just be 3 wild types in a row. The second has fine, so we'll have wild type, and the fine allele. And we'll just do this with all the phenotypes here. We'll write in the frequencies of each of these phenotypes. Excuse me, I missed one right here. So the parental, once again, will be the ones that are most frequent. And the double crossovers will be the least frequent. So to solve part A, determine the gene arrangement for these linked genes. We'll just look at the parental ones here. So our arrangement will be wild type BRF over the AN wild type. To figure out the order of these genes, we'll figure out which one of these genes flip-flopped in the double cross. By looking at our chart, we can find that during this parental gene and this double crossover, the first 2 genes are where they ought to be, but the F has flip-flopped places, so we'll put that in the middle. There we go. Let's figure out the distances between each of these genes. We'll start with the AN and the BR, the first and second, and we'll call this a star. So we'll label the double crossovers with a star, because that's the middle gene, the BR gene crossing over. And then to figure out which is the AN gene, we'll just look for, if we flip-flop the AN gene on this parental version, then we'll find that all 3 recessive will be in a row and all 3 wild type will be in a row. So we'll mark those on our chart over here. So then let's add those all together to find the total recombinant genes, which is 98 plus 87 plus 2 plus 3. That'll be over 1,000 total offspring times 100 equals That'll equal 19 MUs. Now I'll do this with the second set of genes. This was actually the F gene right here. I apologize. So the next set will be the F, and now we'll do the VR. So the double crossovers, once again, we'll mark, and then the leftover genes that we haven't used yet, we'll mark those. And by adding all of those together, we have 26 plus 20 plus 2 plus 3 over 1,000 times 100, and that'll equal 5.1 MUs. So if we draw our map, we'll erase these two up here. We'll get the first gene, the AN, which is 19 MUs away from the F gene, which is 5.1 units away from the final ER gene. All right. Finally, we'll figure out the interference, which equals 1 minus the observed over the expected. So our observed for the double crossovers is 2 plus 3, which equals 5. And the expected, we'll use the decimal form of the distances we got in our map. 9 multiplied by 0.051. We'll multiply that by the total number of offspring to find our expected value, which is 10, approximately 10 in this case. Difference will be 1 minus 5 over 10, which equals 0.5, or 50% of the double crossovers were interfered with.
So question 5 has a couple of questions comparing independent assortment to linkage. And so for part A, we're going to suppose that a cell has the genotype heterozygous A of big A, little a, big B, little b. Assuming that the A alleles are on separate homologous chromosomes, and the B alleles are also on separate homologous chromosomes, what are the genotypes of the gametes produced by the cell, and what is the frequency of each? So in this case, big A, little a are going to be on different chromosomes. Same thing with big B, little b. Again, you can be on little different chromosomes. And so there can work out to be 4 different ways this can work out. We can have a big big B, big A, little a, big B, or little a, little b. And those are going to be a quarter apiece. You can write that as as like a decimal or as a percentage. Anyway, it's going to be 25% each. Part B, we're considering the same alleles. In this case, big A is linked to big B, little a is linked to little b. For this problem, assume that crossover does not occur. So we'll make a note of that. No crossover. And so in this case, A and B are linked. Big A and big B are linked. Little a and little b are also linked. And if there's going to be no crossover, you get 50% big A, big B, little a, little b. 0.5, or 50% each. And at this point, I'm just going to pass it back to Tanner so we can finish the rest of the problem. I don't know. Yeah. Okay.
All right, so for number C, now we're going to assume that a crossover does happen. So we'll take these same chromosomes only we're going to cross over. So we'll cross over right here, and these guys are going to switch. So little a will let it be on the left, big A will let it be on the right. So now our possible gametes are little a, big B, and big A, little b, and those again will be at a 50% ratio. For problem D, it says if the distance between these two genes is 7.8 mu, what is the frequency of each gamete produced in part C? So we can just change mu to a recombinant frequency by dividing it by 100 and getting a decimal form. And this will end up being the probability of one of these genes occurring.
So thanks for reading with us today, guys. Hope this was a good one.